Now, when we're dealing with probability, it's handy to be able to give some kind of label or name to a group of outcomes. And we call a group of outcomes a set. And we often name sets, set A, set B, something like this. Now, if a set is named something like A, then if you see these absolute value brackets around A, then that means the number of members that are actually in that group. And that sort of makes sense, because if you think what is the absolute value of A, then it's just saying, well, how many things are in it? Now, sets can be described using words, or you can list the members individually, but we use curly brackets in general when we're denoting what's in the set. So here's an example. If we roll a 6-sided die and we wanted to describe some particular outcomes that we might be interested in, we could describe them as sets. For example, if we had the set of odd numbers, we could just say the odd numbers, and as long as we've reasoned that we're rolling a 6-sided die and our audience knows that the numbers on the die might be 1, 2, 3, 4, 5 and 6, we could list them this way as odd numbers, or we could say, hey, we're interested in 1, 3 and 5 here. Both of those describe the same thing 2 different ways. Similarly, the numbers that are greater than or equal to 3, bit of a mouthful to write out, you could literally just list them sometimes more quickly, 3, 4, 5 or 6. Now, we also use Venn diagrams to spot unions and intersections between sets. So this same example is reproduced down here in a Venn diagram. I've got a circle for all the odd numbers on the die, 1, 3 and 5 are all in that circle. And then I've got a circle for all the numbers that are greater than or equal to 3, 3, 4, 5 and 6. And you can see that 3 and 5 are in both circles. So we'd say that they're in the intersection between the sets, this section in here. You'll notice that 2 is outside. We always need a box around Venn diagrams because that houses anything that's not actually inside the sets that we've named. Empty sets and equal sets. Well, an empty set is exactly as it sounds. It's empty, it's got nothing in it. And we write it with this symbol. Now, to remember this symbol, think if it's got nothing in there, that's 0. Have you ever seen on a typewriter that 0 and O can actually sometimes be confused? Well, some fonts will actually show 0 with a line through it. And sometimes it's those fonts where the writing is really square and the 0 is kind of rectangular and they put a line through it. Have you seen that before? Well, that reminds me that here we're putting a 0, not an O, okay? And we just make the cross nice and big. So just draw an O, put a line through it and say there's nothing in there. That's how I remember that one. Now, equal sets, nice and easy again. They're exactly as they sound. An equal set, 2 equal sets contain the exact same items. Now, they might be written identically. So you might have a set A and a set B where we've literally got the same things in there. And maybe they're letters, maybe they're numbers, maybe they're people. Perhaps we have Lily and Ellen in this set. And in this set we have also Lily and Ellen. Now, why do we have Lily and Ellen both in the same set? Well, perhaps we've asked some survey question for question A and both those girls put their hand up, and then we asked a different question for B, and again, it just happened to be that both those girls put their hand up. Well, if there's the same people in both sets, then we could say that they are equal sets. We might have written them differently. For example, all integers equal to or greater than 1. That means 1, 2, 3, etc. It could also be described like this. And if you think that those dots look a little bit unmathematical, they're not. It's actually very normal and okay to use dots to show that this pattern goes on. So those two are actually equal sets. Similarly, here we've got items that are letters. Now, if we've got the same 4 letters in both sets, then even though they're arranged in a different order, they are in fact equal sets.